This week in labs, no pre-lab, but pre-lab 5 is already open for you to try out and do for your labs after break. So you can do it before you leave for break, so you don't have to worry about it if you wish. Exam 1, you're getting back in labs. I posted the solutions. I posted a summary of scores, which you'll see in a moment. Also posted a common set of errors. So I had each page leader tell me what was like the most common errors that they saw on their page as they were leading that page, and put them together. So they're up there, also in the exam info folder. Might help you to see why you got something wrong on a certain page when you go over it. Do you need to look it over? Ask your questions you still have the week after break when you come back. So either this week or the week when you get back to address your questions. I'm going to give you a little homework 4 help in a few moments. Homework 5 will go up on Thursday and be due the Thursday after break. We will be completing the material for homework 5 in Thursday lecture. So you would be able to try any of the questions out after that. All right. Here's your summary. Same one that's up on C-Tools. So that's definitely a skewed to the left distribution. The mean is smaller than the median. What I did is I took the 5-number summary, what those actual points were, out of 75 points, divided by 75 to see what percent they correspond to, and then went to the fixed scale to see what grade that percentage would have corresponded to. You can do the same with your actual score. Take your number of points you earned out of the 75, take that to the fixed scale on the syllabus to see what grade you got on exam 1. That exam 1 might be weighted 20% in your final grade at the end, or 0, depending on which method ends up being better for you. So these are the cuts. The numbers for the actual values are just a little different, but these are about the same grades from last semester's exam 1. Kind of compare that. But if you did get 60 points, that's an 80%, and that's AB according to our scale. That was our median. All right, do you have a question or comment at all? Question? Yes? Say that again for the...
lecture book homework.
Mm-hmm.
If it doesn't say show your work, are you supposed to show your work?
In general, if there is some work involved, okay, like if you were taking on your homework 4 question and you were going to work out what proportion of, was it the girls, high school girls participate in sports, and you have to take, 57 out of 100, that's pretty easy to do in your head. I would accept the answer straightforward. But if it were 57 out of 82, I wouldn't be able to get that in my head. I would need to do the calculator. Putting 57/82 would tell me where your number is coming from, so that if you accidentally did the calculator wrong, I might still be able to give you credit for it.
So for like the confidence interval, you would like the equation and then all the work?
If not the full equation being given for your work, at least putting the numbers into that equation so I can go from there. I wouldn't expect you to necessarily put in the full general formula first. But if you have numbers to put in there, put those in. Tell me what your Z star was. What if you looked up the wrong Z star? Hey guys, please. On a confidence interval problem, you've got a couple of them to do in your homework. If you looked up the wrong Z star and just give me your final answer, you'll get no credit for that, because I can't determine how you got your answer. But if you give me your P1 hat and P2 hat, and your Z star, and you worked out your standard error and give me that, I can see where your error came from. And it is worth 2 or 3 points, so you can get some credit for it if you show me some of your work. Numbers plugged in would be good, especially when there is some work behind it. All right, so I did plan to do a little homework for help, kind of guide through a couple questions. That's my blank slide here. How many of you have looked at homework 4, at least worked through some of the questions? I hope. Question number 6. I know you may not have it with you, obviously, but just take a listen. This one is simply working out what kind of mistake would be more severe. And the hypotheses, if you remember, if you've looked at it, is regarding your watch and whether it's waterproof. H0 is that the watch is waterproof. And the alternative is that the watch is not waterproof. And really parts A and B go together. You're supposed to identify which error would be worse and then to kind of explain the consequence of that error, which obviously led to why it's being worse. So, what's the definition of a type 1 error? Rejecting H0 when H0 is true. Rejecting H0, saying the watch is not waterproof, that's your conclusion, when it really is. So you're just a little more careful not to get it wet, but that's not a big deal. Versus what's a type 2 error? Staying with H0, failing to reject H0, when really HA is true. You think and conclude the watch is waterproof when it really is not. Could that lead to some consequences? You go swimming with it, or you get it wet or whatever, and that could damage the watch. Writing that up. Thinking through the definition. So when we ask you to explain the consequences, it's not just what the definition of a type 1 or type 2 error is, but rather the result of making that mistake. What could it be the consequences? Which kind of leads you to pick your Part A question. So that one's not too bad. That's just going through those definitions again. Question number 1. Question number 1, there are 6 questions altogether. Question number 1 is simply making a confidence interval. Our parameter for most of these homework questions, making a confidence interval for P1 minus P2. So the first part of the question is simply checking the conditions. It already tells you you can assume that each sample is a random sample and that our 2 samples are independent. That's telling you that in Part A. So there is one remaining condition. And for proportions, it's always been checking that your sample size or sizes here, more than one, are large enough. So you have to check that at least 10 rule here. Now in confidence intervals, it's basically going to your data and making sure you see at least 10 yeses and nos in each of your 2 samples. That's really all you have to do. Now it gives you the number of yeses out of the total, so you can just go through those counts and make sure each of them are at least 10. And it asks you to verify those. So we're expecting you to give us the number of yeses and number of nos that you saw and say, yes, these are all at least 10. And then to make the confidence interval, which means using your formula, and you don't have to type up the actual formula with the P1 hat and so on, but at least to put in each of the numbers. The standard error will take a little bit of work. If you work that out, at least give me what that standard error is, so then I can see how your confidence interval is formed. And that's all you're asked to do, is to construct it. You aren't asked to interpret it or to interpret the confidence level here. That's question number 1. Question number 2 is about the high school girls and boys participating in sports. And you're given the table of the counts this way. How many said yes, how many said no? And your first question for making a confidence interval, again, is to check the conditions. So it's pretty straightforward, just like your first one in Part A. And you can simply look at the counts in that table and say, yeah, they're all at least 10, but write that out. Now, Parts B, C through the end. Wow, that's a long question, isn't it? Lots of true and false. But have to do with, then, do you understand what the confidence level means and what the interval means? All right? Some of these say the chance. There's a 95% chance that the true difference is in your interval that you make. And actually, you don't even have to make it. I give you that interval. But do we talk about chance or probability or likeliness in terms of the one interval we made? No, those usually end up being wrong. There's not a 95% chance that the true difference in proportions is in the interval, because it's either in there or it's not. If you want the chance, it's 0 or 1 idea. So working through those. They talk about if you repeated the process, what do you expect? And again, it's expecting that 95% of the intervals. Not your interval having the true difference in there, but 95% of the possible intervals. So just reading through each question and understanding those, true or false, selecting. One of them talks about what if you wanted to be 90% confident instead of 95% confident. So if you made a 95% interval, and you're going to make a 90% one now, what's going to happen to that interval? It's going to be narrower. And just working that out. So those are just a series of selecting the right answer. The one other item I'm going to mention, the confidence interval is given for you. The confidence interval for the proportions, being the difference in proportions of girls versus boys participating in sports, was a negative 0.05 and plus 23. This interval was computed for you and given to you and used in some of those true-false statements. But when you're dealing with the difference between two proportions, what number are you typically looking to see if it's a possible value or not? 0. What would it mean if P1 minus P2 could be 0? That means those two proportions really could be the same, no difference. And so one of the questions is talking about whether you have a significant difference or not. And you're really looking for to see whether 0 is reasonable or not, and is 0 in our interval? Yeah. So you would have to support, you could not refute a value of 0. P1 minus P2 could be 0 according to your data at a 95% level of confidence or a 5% level of significance. And so that's one that you need for that last question, part H. You actually can test a hypothesis of whether 0 is reasonable or not by simply looking at your interval. All right, questions 3, 4, and 5 are all on the same data. Questions 3, 4, and 5 are about comparing some new treatment X to a standard treatment. And the first analysis takes the data from this experiment and makes a confidence interval. You have to compute the interval. Oh, no, excuse me. Is that right? Yes, make the confidence interval. You define P1 and P2. So one of your questions says, give me the definition. Both of those definitions should start with at least a few words at the beginning for sure, and then you complete it. P1 is what? What kind of proportion is P1? It's a population proportion. It's the population proportion of all such patients who get whatever standard X treatment that would respond favorably, whatever it is you're measuring. Make sure you talk about the population proportions. You're asked to define them in terms of what proportion of all patients would be cured, and then to make the confidence interval. So one more practice at that. Again, I expect a little bit of work in that making of the confidence interval, not just the final answer. You won't be given that. You need to show some work to get that interval because you had to do some work. But it does ask you, once you get the interval, to decide whether you have a significant difference or not. And we just commented on how you'll do that. You'll look to see if 0 is in your interval. If 0 is in your interval, do you have a significant difference? If 0 is in the interval, then there is no significant difference, because it could be that those two proportions could be the same. Only when the entire interval is positive or the entire interval is negative do you have a significant difference. Now, when you make a confidence interval, say 95%, you're putting 95% in the middle, right? And kind of finding the two numbers that give you your interval, acceptable values inside here. Anything that's inside here is acceptable. You can't refute it. Anything that's outside here or here, you would say not reasonable, right? Anything outside the interval is not a reasonable value for that parameter. Inside the interval, it is acceptable or reasonable. This is going to have how much in this tail? If there's 95% in the middle, about 2.5%, and another 2.5% over here. And can you kind of see that if you're doing a confidence interval, it's somewhat similar to what you do when you do a hypothesis test that's of what type? When your HA is two-sided. Because you kind of shade two tails and you find those two p-values, adding them up together. Now, when you are asked to do question 4, you're asked to do a hypothesis test about whether P1 is equal to P2 versus the alternative is given for you as being a one-sided test. And you have to go through that whole test. So that's a pretty long question. You have to calculate P1 hat and P2 hat, which you've done in question 3. But then you have to do the Z statistic and find the p-value. I think you have to draw a picture for it too. Is that right? Is that the one upload that you have? Yep, we need a picture. You're going to calculate a z-statistic, right? And get some number. What model do you think of for your z-statistic if h naught's true? What model do you start to draw to find the p-value? The standard normal, the normal 0, 1. So that's a picture you have to draw, and then you have to shade in what your p-value corresponds to. But when I think of a z, I think of a normal 0, 1. This is the right model for your z-statistic if h naught's true. This is your h naught model for your test statistic. And what does the question after that ask? Not what is the model for your statistic, but what's the expected value for your test statistic? Expected value is just another fancy word for mean. There's the model for your test statistic. What's the mean for that distribution, for your test statistic model? That's it. Did you get it? The mean is what? 0. You would expect your z-statistic to be 0 if h naught's true. Your z-statistic looks at p1 hat minus p2 hat on top over a standard error. If h naught's true, the two proportions should be the same, so you'd expect these two guys to be the same under h naught. So you'd expect 0. All right. Now, when you do your test in question 4, though, what is the direction you're doing here? You're doing a one-sided test, one-sided to the right. And if you do that test at a level 5%, it's equivalent to putting in your upper tail the full 5%, not 2.5%. And so you find some cutoff, and if you're out there further, you're extreme enough to reject, and if you're not, you stay with h naught. Do you see there's a difference between then your confidence interval and the test that you're doing? That you're doing a confidence interval that's like a two-sided test. When you're doing a one-sided test, you're putting all of your alpha in that upper tail. So there's these values right here that kind of fall in between, that in one case you would reject, but in the other case you would not. What I'm leaning to is that question 5 says, is your decision about whether there's a difference between these proportions the same through your confidence interval as it is through your test? And it's not. In your confidence interval, you should get an interval where 0 is inside that interval. But when you make the hypothesis test, you would say, no, I don't think h naught's true. I'm going to reject h naught. You'll make what seems to be a contradictory decision, but because one is two-sided and the other's a one-sided test, you're not doing the same test. And you're asked to reflect on that in question 5. So you go through and do the confidence interval, you go through and do the one-sided test. In one case, you say, I can't say there's a difference between the two rates. And in the other one, in the hypothesis test, you say, yes, there is a difference, and P1 seems to be bigger than P2. That's because that's what you were looking for. You're putting all the evidence towards looking for one direction, and there was enough when you were only looking in one direction and not splitting it up. So I'll let you think through that, but that's what your conclusion should end up being. And those are your 6 questions on homework 4. All about two proportions. Homework 5 will go up on Thursday. It'll be about the means, and that's what we're studying a little more today and a little bit on Thursday. Questions? Let's take a look at our notes. Page 117. Page 117 is your box at the top. We have started to work through our third parameter, third of the big 5, and those big 5 parameters will be what your exam 2 will be about. We've already handled proportion P. Your homework 4 is taking you through P1 minus P2, the difference in two proportions. And now we've changed over to when our response is quantitative. So we want to learn about the mean, the average score, the average reaction time. And one thing we might want to do is estimate that mean. So one way to do that is through a confidence interval. A confidence interval estimate for what the true mean, mu, might be. We'll take the data that we have, which has to be a random sample from our population. We'll calculate our sample mean as our best guess. And then we'll go out reflecting the fact that a sample mean doesn't always equal a true mean. It varies. We'll go out a few of those standard errors. A few of those standard errors of the sample mean. The few now, though, is a t-star. And that is because when we were looking at this standardized quantity, subtracting the true mean, you'd like to divide by the true standard deviation, but sigma's not known. And we have to put in the S. We have to use the standard error in the bottom. And we were able to still use z's when we did proportions because we required a sample size being large. But here we're not going to require the sample size be large. It doesn't need to be large. We need to have that we have a random sample of any size coming from a population whose model is normal. The large sample size can be helpful if that normality condition seems to be not quite there, relying on the central limit theorem, but it doesn't require large sample size. So whenever we have to use the standard error, this quantity now has more variability in the bottom, and it was called a t. We introduced the t distribution last week, which looks very similar to a normal, standard normal, but it's got a little thicker tails, allowing for a little more variability lower in the middle. We learned how to look up t-star values with our table A2 with appropriate degrees of freedom. The degrees of freedom are n minus 1. That comes from our S. Your formula for S has an n minus 1 on the bottom, that associated degrees of freedom. All right, we made a confidence interval. This was for those 15 drivers. Did that on page 118 or 119 and 120. We ended with the output together, which you're going to see a lot more of on exam 2, especially with means, because calculating standard deviations with data is not as nice by hand. Your pre-lab 5 will take you through the 2 ways to get a confidence interval for a mean. And you have to pick one of those ways to do for your pre-lab assignment, generating one confidence interval. Here was our confidence interval for the average maximum distance. Still had to interpret the interval and had to interpret the confidence level, as we did on that page 120. So confidence intervals allow us to get a range of values that would be reasonable for the true mean. Anything from 456 to 537 is reasonable. I would have to accept those values. So we're going to turn to the testing side now, where we're going to be doing not a z-test, but a t-test. Let's step through a few of those basic ideas again. Remind us of those 5 hypothesis steps, starting on page 123. This is chapter 13. The first time we've gone into this chapter, which is about means. There's a couple of notes of caution. If I remember, I think one of your true-false on homework 5 is about one of these notes. Pretty basic. I mean, if you take your sample, the inference that we extend can only be extended to the population that our sample represents. If our sample consists of only males, we can only extend it to the larger population of such males. The hypotheses or conclusions only apply to those larger populations. And we require that we have a representative sample. What we're going to run into is sometimes our QQ plots that we'll make for our data, now that we have quantitative data, the QQ plots will show some departure from normality. Maybe it's highly skewed, or there's definitely some outliers. In the case where your sample size is large enough, we're going to have that safety net, that central limit theorem, that we'll be able to rely on and say, that gives me the free pass to still do the T procedures. But in the case when the sample size is not large and we've got skewness, we're going to have to think about not doing our T procedures, but going back to analyzing medians rather than means. And we'll name a couple of those tests as we go along that allow us to do that. Medians are more resistant to skewness and outliers than our means. So those are just a couple of notes. And then they step you through a review of the 5 basic steps for hypothesis testing. So we're going to be stating some H0 and HAs again today. They are always statements about your population. In this case, the parameter we're trying to learn about is the population mean. We'll have some conditions that need to be checked, as we do for doing tests about proportions. We would also have conditions about means. When we're doing proportions, what kind of statistic do you calculate? When you're doing question number 4 on your homework 4, you're going to be calculating a Z statistic. This is, of course, when your sample size is large. And I've already asked you this question today. What model do you use then to find the p-value if you're doing a Z test? You can either write it as the normal 0, 1 or call it the standard normal. But when we're working with means, whether it's one mean as we're doing today, or after break when we talk about 2 different means or differences in means, then our statistic is going to be a t statistic. And we won't be able to use our table A1 anymore. The model for a t statistic has a clever name. It is a t distribution with a certain degrees of freedom. The degrees of freedom we have so far is based on a single sample, just the n minus 1. What do you think is going to happen when we go to 2 samples? Just like we went to 2 proportions and took a sample from each of boys versus girls, what if we were doing something quantitative? So we have a mean mu1 and a mean mu2. If you have sample size here and a sample size here, your degrees of freedom would be an n1 minus 1 and an n2 minus 1, and we'll add those together for total degrees of freedom. All right, so we're going to have to work with t distributions. We're still going to have the same basic steps. We'll find a p-value. We'll show you how to do that today with your new table A3. But once you get the p-value, from there on out, the decision process is the same. Because you converted whatever distribution you're working with, whether it's a z, a t, a chi-squared later, or an f, you're going to get a p-value from it. And that p-value is used to make your decision in the same way. You get a statistically significant result if your p-value is small, less than or equal to alpha, and then you're able to reject H0. Then we'll have you write up a conclusion. One thing you might want to note, your conclusion should always be about between H0 and HA, right? And those are statements about the population, not the sample. So your conclusion needs to be clearly stated that you're talking about in the population. I expect there to be a majority. In the population, I expect the average to be higher than 20. Something about the population being concluded about. You have a nice little table. We'll fill that out before we move on to doing our actual t-test. It just reminds us that this p-value, which is always between 0 and 1, because it's a probability, gives us some idea of how much evidence we have. What if you did a test and your p-value was huge, 0.46? That means if H0 is true, the chance of seeing the results that I got, or more extreme, would happen almost half the time. That's quite likely to happen under H0. So we're definitely going to stay with H0, fail to reject it. In fact, we might even say that we're not even close to significance, and that theory in HA is not supported at all. There's actually not any strong support for that alternative. There's no reason to continue to look into that new theory. There's really no support being given. But what if your p-value is large, but not that large? It's still bigger than 5%, like 0.06. So you still can't reject H0. But isn't there a difference between those first 2 entries? That second one of 0.06 says, okay, you were close, but not quite. You were just missing being significant. Some write-ups that I used to do for some companies say this, report this as being marginally significant. Whenever it's between 0.05 and 0.10, that's marginally significant, close, approaching significance. It might be that there's really something going on there. It might warrant repeating that study with maybe a larger sample size. It might be that even though you weren't statistically significant, that effect that you saw there was practically important. It's still meaningful from a practical view. It might be that this was a pilot study, so you should get the funding, hopefully, to go on and do a larger scale study to have a more powerful test to possibly detect that effect that seems to possibly be there, but you couldn't deem it statistically significant. And then if you sit just on the other side of 0.05, of course, you have crossed that cut, how much evidence you need, and you are significant at a 5% level. There's sufficient support for that new theory. There's really not much difference between 0.06 and 0.04. You just are on each side of that cut. And again, 0.04, you reject H0, but so would you for anything smaller, even like 0.003. That's not just significant. That might be called highly significant. Very strong support. The smaller the p-value, the more support for HA. So just saying you reject or you fail to reject is not so good to report without also giving the p-value. So you can see how much evidence was really behind that decision you made. Good. Most journal articles require you to report the p-value. They don't require you to report the formula for the test statistic or what its value is, but they report the p-value so that you can know the degree of evidence that really was there. All right, let's turn to then doing our testing about the mean. The background again, one population of interest. My response isn't going to be a yes and no answer anymore for a proportion, but it's going to be a quantitative response. I'm wanting to learn about the mean. I want to test a theory about what the true average response might be. I require that you take from that population a random sample representative. I don't require a large sample size. I require instead that the population is normally distributed. Because if my population has a normal model for that response, no matter what sample size I take out, the sample mean, x bar, will be normal too. That's the sampling distribution of the sample mean. We have this little caveat at the end. If your sample size is large enough, though, that normal model for your population isn't quite as crucial of a condition. And why is that? What's the result that allows you to say, don't worry about that normality condition as much if you took a large sample size? Central limit theorem. It doesn't say that your population is going to become more normal just because you take more data from it. It says if you take more data from it and calculate x bar's model approaches normality with larger and larger sample sizes, and that's what you need. So we're not requiring a large sample size, but we have the safety net that if the sample size is large and we look at that QQ plot and it's off a little bit, we're still okay to do our t-test. We're testing about the population mean. You should never see an x bar in your H0 and HA. It should always be about that true population mean mu. H0 always has what symbol in it? It's always got the equal. It's your status quo value. Before we had like a P0 to represent whatever that number was. So here we're going to have mu0. You will always put a number here based on the actual problem at hand. And it's the alternative theory that might be a direction. It might be that looking for values that are large are better. So one-sided to the right. It might be that you're looking to hopefully reduce your time to feel better, your time to relief. You want it to be smaller. And that would indicate better. Or maybe you're looking for a change from some target value. It's supposed to have an operating at some mean, and you want to know if you're off in either direction, so you're looking for any change at all, two-sided. It is your HA, again, that will dictate how you draw your picture for your p-value. Now, we have some conditions. Random sample and a normal model. One is about the sample, one's about the population. How would we check them? How would you check for a random sample? Well, sometimes we just tell you, assume you do have a random sample, because it really is based on how the data was collected. It depends on the study design, which we either have to give you a lot of detail about that, or we just say, let's assume it's okay. So it does depend on the study design. I mean, if it was a study in which you simply accepted volunteers who looked at your ad in the paper about, do you suffer from migraines, and you come in to possibly be part of this clinical trial, you might have to look at some factors about those people that are in to see whether that's really representing your general population. There is one other thing you could do. If your data were collected over a time period, not all at once. So I had some measurements being made over the next week, and I collected that data over time, and I had the time element recorded. Then what kind of graph might I use to make sure that I've got observations that are identically distributed or approximately stable? A time plot. If your data is collected over time, you've got a quantitative measure that you could do a time plot for. And if that is the case, you'd want to see stability being supported in your time plot around a common mean and a common amount of variability. If you didn't, it would not make sense to calculate a mean of that entire sample or to treat it as one random sample. All right, the other condition is about the population. The model for the population is normal. How might we check that? You can't go to the population and take all of those measurements and make a QQ plot or histogram of them. If you did, then you would also be able to calculate the overall mean and have the true mean. But you took your sample from there. So you're going to at least make a histogram or a QQ plot of your data. You're checking whether the population is normal by making a graph, an appropriate graph of your sample. So we would make perhaps a histogram, but certainly a QQ plot. And we know what to look for in those two types of graphs. Histogram may not work very well if you only have observations on 5 frogs in your biology study. That's not much data to make a histogram of. But a QQ plot could still be made to see if they at least fall along the right percentiles for a normal curve. The test statistic then that we will be able to compute. What are we going to do? We're going to look at our sample mean. And how close is it to that hypothesized value for the true mean? How close is it to that hypothesized value? Of course, I have to look at it relative to the right yardstick. You know, a distance of 1 may not seem big, but if it's 1 inch versus 1 foot, one looks bigger than the other. So you need to have it not really depend on the units. So we divide by our standard error. I'd like to divide by S over square root of n, or sigma over square root of n, but I don't have sigma, so I'll have to put in there the S, the sample standard deviation. And this is called a t statistic because it's going to follow a t distribution with n minus 1 degrees of freedom. It's because the standard error is down there and I'm not requiring a large sample size that this does not follow a standard normal, but a t distribution instead. Got some nice pictures on the top of the next page to show you the p-value ideas. We're going to follow these basic steps when we do our examples in a moment. But the table we're going to have to use now is table A3 for finding p-values for t-tests. Once you get your p-value, you make your decision the same way, and you write up a conclusion. So that's the overview. Take a look at your table A3 on page 127. So when you were doing table A1, which gave you areas to the left of any value of z that you wanted to look up, there was only one normal curve that you were dealing with, the standard normal. We have t distributions with 5 degrees of freedom, t distributions with 27 degrees of freedom, any degrees of freedom that's possible for any sample size. So we need a separate table for each one of those if we want to have as much accuracy as we do in table A1, or instead we just give you a few values so you can look up the p-value bounds rather than the exact value. And usually that's sufficient so you know if you're bigger than 0.05 or not. So what you have are degrees of freedom along the first column. So we'll figure out which row are we going to be in. We'll have a particular row. And then we'll look along the top and say, what was our t statistic? oh, our t-statistic turned out to be 2.8. 2.8 is not right here, but it's in between. And so if I fall in between two columns, I'll look up that same row, those two values, and those will be the bounds for a one-sided p-value. And of course, if you're not doing a one-sided test but a two-sided test, what are you going to have to do? You've only got this part, that's half of it, so you're going to have to double things. But we'll be working with the table, reporting bounds, drawing our pictures. So let's try two examples out before we do a full t-test together. Just practice on the p-value side. So you're given the hypotheses, you're given the number of observations, and the sample mean was computed, the sample standard deviation. The t-statistic was found for you, 1.97. We're asked to complete the testing part by finding the p-value. So step number 1, you calculated a t-statistic. Draw me the picture of its model, its distribution under H0. If it is a t-statistic, then you're going to sketch for me a t-distribution, because that's the model for a t-statistic under H0. But which t-curve are we using here? It needs to be indexed by the degrees of freedom. So there's 15 observations or 14 degrees of freedom. Now, t-distributions are also centered at 0, just like the standard normal was, but they have a little thicker tails compared to a standard normal, a little bit lower in the middle. I don't draw them much different than my normal curve, so I always have to label what curve I'm working with. Now let's place on there what you observed. What did we observe for test statistic? It was 1.97. So there's my observed value of my test statistic. And then I want to show in the picture my p-value. I need to show the probability of getting what I did get for my test statistic or something more extreme. What direction will be more extreme here? Depends on what your HA was. And what direction was HA telling you to go? To the right. So my p-value will be the probability of getting what I did get for a test statistic or something even more extreme, which would be larger. So this shaded area is what I would like to find. That's our p-value. So there's the picture of it. Now you go to the appropriate table and find that p-value. So our table, you have to maybe flip back a page. We want to look at the row with 14 degrees of freedom. And you have a couple of values of a t-statistic along the top to work with. It would be really nice, of course, if you ended up getting to be exactly one of those values, because then you just look up that number in the column and that's your p-value. But if you don't, you fall in between, which we do here. And so these two values that I have are going to be bounds for my p-value. What that means is if I were to take the 1.8, which is a little bit smaller, that's in the chart though, and its area to the right is a little bigger than my p-value, but I have it. It's 0.047. 0.047 is the area to the right of the smaller number. So my p-value is smaller than that. I can even be a little more specific if I take the other bound, which is pretty close to actually. 2 is very close to my test statistic value. And from that 2 all the way over to the right is how much? Only 0.033. So the p-value that I want is a little bigger than 3.3%, but I know it's smaller than 4.7%. It's in between. It's even closer to the 3.3% because I'm closer to the 2 than the 1.8. So I can report the bounds for my p-value. Our p-value is between 0.033 and 0.047. So we aren't able to be specific and give you the actual p-value, but can you use it to still make your decision? Here's our one-clicker question for today. Using your bounds for this p-value to decide if you are statistically significant or not. We can't report the p-value exactly, but we do know two numbers that it falls in between. You're still asked to do the test at a 5% level of significance. So now it just takes a little bit again on the number line. Make sure you know where you fall relative to 0.05. And you're getting better. So got a few in the wrong direction. Is the value of your t significant? Is your p-value what? Less than or equal to 0.05 is what I'm really asking. And indeed, most of you are getting it correct. We are smaller than 0.05. Since we're smaller than 0.05, we can reject H naught and say we're statistically significant. I wasn't able to give you the exact p-value, but you can still make the decision. Most places in your table, you should be able to do that. There's a few places in your table where the 0.05 actually would be in between your bounds. That's usually happening only when you have a really small data set, like 3 or 4 observations. So it doesn't happen very often, but if it does, we have other ways of getting the actual p-value known. We'll see it in the output provided for you exactly, or you have tables that are more detailed, but we are able to make the decision. Can we even make the decision if it were 1%? What if your alpha were 1%? Would you be significant at a 1% level? Yes or no? Not at a 1%. So we're significant, but not highly significant. Our p-value is less than 0.05, but not less than 0.01. And we'd be able to write out a conclusion. All right, you get one more practice. Please draw a picture for the p-value for that last problem on this page. It's a two-sided one. And work with your neighbor to use your table to find the bounds you can for that p-value. Give you a minute or two to try that one out. All right, for this question, you have not a one-sided test, but a two-sided. You have a test statistic that happens to be showing you an example of falling off the chart. You're not in between two numbers from the column headings, but you actually fall off the chart on one side, and you could, of course, fall off the chart on the other side, too. So we have a 29 degree of freedom t-distribution we're working with, which we do have in our table. What would happen if our degrees of freedom, though, were like 33 or 42? If we fall in between, which we will if it's anything more than 30. Then we're going to use which degrees of freedom? The one going closest to it, or do we always go to the smaller? Always use the smaller degrees of freedom if you do fall in between. We've got 29 degrees of freedom. We've got 1.12. Our sample mean was only a little more than 1 standard error above the null value. That's extreme, but so would it be being that same distance below the null value, because it's a two-sided test. So those two tail areas together make up the p-value. Now, I didn't draw it very well to scale, but those two tail areas, of course, are the same. They're symmetric. So I really need to find what I can about one tail and do what to it if I want the other one also. Double it. So we fall off the chart, and the closest number we have, the smallest t-statistic value listed, is 1.28. What do you know about the area to the right of it with 29 degrees of freedom? 105? That's the bound for your one-sided p-value. We want the bound for our complete p-value here. What can we say then? Our p-value is definitely big, isn't it? It's greater than how much can you say for sure? It's greater than twice the 10.5%, or greater than 0.21. Your p-value is large. Half your p-value is more than 10%, so your total p-value is more than 20. It's more than 21%, and that's quite big. If you want to bound on the other side, what p-value? P-values are always between 0 and 1. So it's more than 21% but less than 1, or 100%. If a p-value is that big, what will be our decision? Without even having an alpha, your general alphas of 1, 5, or 10% would lead you to? We would typically fail to reject H0. We are not statistically significant at any reasonable level of alpha. At 5%, 10%, 1%. If we ever forget to give you an alpha and you're asked to do the test, say we'll use a 5% level. I mean, that's a common one that can be used. All right, so there's a two-sided one. We'll do one more example of a lower-tailed one during our last question together, page 129. Now that we've worked with the table a little bit, here's your picture of the day. It's one of my favorite. It's my husband taking my daughter out to the Lake Michigan. Her feet are not touching. I happened to take the picture right when she was, it's cold, right? And she was jumping, so her feet were not touching, which is just kind of cool, hopping. All right, it would be very cold today. Classical music. When my boys were very young, and they'd bring home their little bit of homework from elementary school, I would have sometimes classical music or just nice music playing in the background in the kitchen, and they would sit up to the counter and work on their homework, giving a nice area to do their work. Are you able to think? Are you able to complete a maze more quickly if you were listening to classical music than not? That's the researcher's question. Asking that question for the population of high school students. So there's this maze, a standard maze, and the time to complete that maze for the high school population follows a normal model with usually an average of about 40 seconds. So the typical time to complete the maze for high school students is about 40 seconds, and there's a give or take there, the normal distribution. We would like to test the theory that if you gave this to high school students, that their average time to complete the maze would be faster, less, if they're listening to that classical music. Do that test at a 5% level. So what are we doing? We're measuring time to complete the maze. That's quantitative. Mu represents then the population mean. The population mean time to complete the maze I'm still missing two aspects to define that parameter correctly. It is a population mean time to complete the maze, but I need two things. First of all, it has to be the population mean time to complete the maze while listening to classical music, and for which population? For all high school students. Those two aspects need to still be there. It's the population mean time to complete the maze while listening to classical music for all high school students. I can imagine my basket being all high school students and a ball for each person in that basket being their time to complete the maze if they did it while listening to classical music. And I'm trying to learn about the mean mu for that population. All right, can you write out the hypotheses, the theories? H0 would be the status quo. The statement that the treatment, the classical music being played, would have no effect on average. So what would that mean about our population mean? The population mean would still be about 40 seconds. Right? If there was no effect, then they should still complete it on average in about 40 seconds, because that was the established status quo for that maze. What is the theory we're trying to put to the test here? They would do it more quickly. Does more quickly mean larger? No. More quickly in time means less. So watch that the direction here of more quickly doesn't mean it's greater than. It actually means the time is smaller. So there's the hypothesis. It's one-sided to the left. Now we have the data coming in. 100 high school students are given the maze, and they complete it and are measured how long it takes them while listening to classical music. For those 100 high school students completing that maze, their average time was 39.1 seconds. So what is that? Is that mu, the true mean? It's an estimate of the true mean. It is based on our sample, so our notation for this would be what? X bar. We've got X bar of 39.1, and the fact that that is below 40 tells me there's some evidence there. It makes sense to do the test because there is some evidence coming in. What if that sample mean turned out to be 42 seconds? Would you even need to really do the test? I want to know if it's less than 40. Comes in at 42. Well, it's obviously not going to be less than 40. And your p-value would be much more than a half, really large. But here there is some evidence. And we also have a measure of the standard deviation of your 100 observations. So that is your S, sample size of 100. So let's do the test. We need a test statistic first, and then we need our p-value so we can make our decision. Our t statistic, here's the formula, one way it's written on your yellow card. It measures how close your 39.1 is to the hypothesized 40. It measures that in standard error units. Negative, because we're below the mean, negative 2.25. Our sample mean was more than 2 standard errors below 40. It was 2.25 standard errors below the null value. Is that some evidence there? Even though this is not a standard normal, they're pretty close to standard normal curves, those t-curves, so you can still think of 2s or 3s or larger being somewhat extreme. Let's measure how extreme that is through the p-value. So one more picture today of a t distribution. Your model for your test statistic under H0. How many degrees of freedom will I have? 99 degrees of freedom. That's not in your chart when you go to look it up. You're going to have to approximate that with the 90 degrees of freedom. Even though you're closer to the 100, the numbers down at the bottom, they'll get hardly any different when you move from one row to the next. We have a t statistic of negative 2.25. And I want to find the probability of seeing that kind of a value or something even more extreme than that if H0 were really true. This is our p-value. that little area to the left. Now your table is set up and there's no negatives, but you really have a symmetric distribution. So instead of working with the right tail areas, you can think of all those t's along the top as being a negative and do the same thing for finding the bounds. So your table A3 again, working with the 90 degree of freedom row, and I'm going to get close to 2.25. I will fall in between again, a couple numbers. Pretty soon you won't have to necessarily write down those values, but just the bounds that you would pull off from there. But I do have a -2 and a -2.33 that I'm working with in my table. And with 90 degrees of freedom, I can use those two values. The larger area is 0, 2, 4. And that area to the left of the -2.33 is even smaller, 0, 1, 1. What can you say about your p-value? It's between those two numbers. You can write it this way with inequalities. That's one way to report it. Sometimes students get the inequalities going in the wrong direction or they put the wrong number. You can say it in words too. The p-value is between 0.011 and 0.024. Can you still make your decision? Can we still answer our last couple questions? Our p-value is quite small, for sure less than 0.024, and we're asked to do the test at a 5% level. Are you okay with finding the p-value? That's working okay? Bounds when you use the table next week or after break, or maybe on Thursday. We'll see an output example where you see it directly. But are we statistically significant then at a 5% level? Yes or no? Yes. If you have to give a brief explanation, it's because our p-value is less than or equal to 0.05. Now you can't use that explanation if you didn't give me a p-value. So that's why I've mentioned that if you're working through and you can't get the p-value, don't have time to complete that, put a p-value down and use it to make your decision. I can give you credit for that. State your conclusion at a 5% level. This is back in terms of the problem. So do we have enough evidence to support that researcher's claim? And that researcher's claim was that the population mean time to complete the maze while listening to classical music for high school students was significantly lower. Something along the lines, but it should be about your population. There is sufficient evidence to say the population mean time to complete the maze while listening to classical music is lower than 40 seconds. This would be for the population of all high school students that our sample represents. In our population of high school students, we would support that the mean time to complete the maze has been significantly reduced. Again, those are all kind of statements, but are talking about the population mean. We aren't saying that every single high schooler would be able to complete the maze more quickly. We're saying that on average, for that population, that mean time would be reduced, less than 40. Assumptions is our last comment before we're done. We're told we have a random sample of high schoolers. Certainly, if this were only high school seniors, we could only really extend it to that larger population. So the random sample was given. What was the other condition again? Not about the sample, but about the population. The model for the population needs to be normal. Now, the population model for times to complete the maze without classical music was said to be normal. So it's probably reasonable to have it be for when you are listening to classical music. But what would you probably do to check that condition. So we're told we have a random sample. How about the normal model? Normal model for our population. What could we do? We could make a QQ plot of our 100 observations or a histogram. And what if we make that nice QQ plot and our points start to fall significantly off the line? Is our inference that we just did invalid then? Or what could we rely on to say, no, it's okay, your results are still fine? Sample size is 100, larger than this sort of magical 25 or 30, but that is the mark that tends to say, even if you have non-normality for your response, times to complete the maze don't look to be normally distributed, you're averaging 100 of them. And averages of that many observations tend to follow a normal model. So you would be okay by the CLT. Inferences would still be valid by the central limit theorem. We'll finish out these notes on Thursday.